During the cell life, hello? During the cell life, DNA is damaged more than 70,000 times for 24 hours with different type of damages. That's why cells develop DNA repair mechanisms, which include more than 300 proteins to prevent genomic instability and cancer. However, most mutagens generate diverse type of DNA damages. For example, reactive oxygens have base modifications, single and double strand breaks. UV radiation make UV damages in single and double strand breaks, and X gamma rays also generate diverse range of DNA lesions. Given that different DNA repair pathways may be active with the same DNA regions, mechanism must exist to ensure correct spatial and temporal coordination of the repair process. We use Hela-Kyoto back-tack cell lines with AGFP-tagged proteins which are under control of their own regulatory sequences. We use UV laser microirradiation to generate complex DNA damage in the small locus in the cells. And you can see the proteins are recruited on the place of the damage, and we can take the intensity profile of this recruitment. We succeed to have intensity profile for 70 proteins, which are recruited on the site of complex DNA damage. We succeed to fit them to consecutive reaction change model, which represents protein dynamics to recruitment with several consecutive reactions, which stay and the protein stay for given period of time, and after that is removed from the site of DNA damage. We also succeed, some proteins are recruited to two or more several to separate mechanisms, and we can fit to two or more CRC models actually to have separate kinetics of the recruitment. After that, we cluster all these proteins on the base of their half-life of recruitment, and we obtain several clusters. We overlay these several our kinetic data with the available protein interactions to have to obtain temporal map of the protein interactions during complex DNA damage repair. And what we saw at that we have some master regulator which interact with most of the protein in given period of time. Such protein is PARP1, which interact with the protein which are recruited early during the DNA damage repair. Such after that is coming PCNA, and who interact with the most of the protein from the 2 to 5 cluster, and ubiquitin. The last protein which are recruited on the site of DNA damage are protein which participate in homologous recombinations. Okay, this is kinetic of the recruitment and removal of the proteins. I don't have time to compare all of them, and I will point your attention actually of three phenomena. The first one is that protein which participate in error-free DNA synthesis are recruited early, then the protein which participate in translation synthesis actually. And the second one is that two proteins which participate with each other to recognize UV damage, DDB1 and DDB2 actually are recruited in different time, and DDB2 is considerably faster than DDB1. And finally, the protein which recognize double-strand breakage is recruited considerably early than RPI, which means that DNA resection is coming 600 seconds slower than after recognition of double-strand breaks. When we have the kinetic of this protein, we decided to see if it's possible to test actually anti-cancer drugs on the base of the kinetic of the recruitment of DNA repair proteins. because some of the anti-cancer drugs actually target DNA repair. Such anti-cancer drugs are PARP inhibitors, and several of them are already on the market. Actually, what we test is the PARP inhibitor talazoparib. You can see that some of the proteins already are not recruited on the site of DNA damage, and this is the fast protein which depends for poly-A-ribose, which PARP1 is synthesized actually. But you can see that also treatment with talazoparib significantly delayed PARP1 itself, and without PARP inhibitor, the PARP stay on the site of DNA damage only for 30 seconds, but if you put talazoparib, he stay for more than 600 seconds, which confirmed that PARP is trapped. But with this type of experiment, actually we can quantify this. You can see these proteins, which depends from PARP, is removing from poly-A-ribose, and PARP1 is trapped. The second event which I would like to point your attention is that PARP inhibitor significantly delayed pCNA and proteins which participate in error-free DNA synthesis. And in this case, with PARP inhibitor, they already came with proteins with translation synthesis. You can see this more precisely actually. And our results give us three important questions actually. What is the mechanism ensuring the windows of opportunity for the error-free DNA synthesis machinery to repair DNA before the recruitment of error-prone translation DNA polymerases? And why does it disappear following PARP inhibition? Why is DDB recruited substantially delayed compared to DDB2? And third, what is the reasons that DNA entry sections and homologous recombination is significantly retarded compared to the recruitment of double-strand break sensor? And for first, you can see here after the talazoparib, without talazoparib, the error-free polymerases come early than translation synthesis polymerase. But if you put talazoparib, they come two at the same time. To study this more precisely, we use we use cells which simultaneously express pCNA label with cherry and the given DNA polymerase. And you can, in this case, we can measure that proteins which are recruited translation synthesis polymerase actually are recruited 60 seconds later than the other one. But also, what is more important, that RAT18 also is delayed in such way. RAT18 actually is required for recruitment of translation synthesis polymerase, because RAT18 have to monoubiquitinate pCNA to stabilize recruitment actually of the translation polymerase. But actually is not known what recruit RAT18 to the site of DNA damage, because we would like to see what is the reason for this delay of translation synthesis and of the RAT18 recruitment. We checked because RAT18 is recruited with ubiquitin in the same amount. That's why we would like to see if the polyubiquitination, which actually polyubiquitination is the reason is necessary for the recruitment of RAT18. And polyubiquitinations actually happen because of double-strand break repair, not for translation synthesis. To do this, we use mutated ubiquitin with mutated of all 7 lisands, which prevent its polyubiquitinations. And we co-transfected this with histone 3, which means that the cells in blue are overexpressed with this mutated ubiquitin. As you can see with the movie, overexpression of the mutated polyubiquitin diminished more than 30 times recruitment of RAT18, but not of the pCNA. The same actually is the result with POL-H. POL-H is already not recruited to the site of DNA damage, but pCNA is recruited. This means that polyubiquitination during double-strand break repair is necessary for the recruitment of RAT18, and only in this case the translation synthesis protein which participate in translation synthesis can be recruited to the site of DNA damage. And this is the mechanisms actually. You have normal DNA synthesis, but when the normal polymerase meet the let's say UV damage, then have to wait for the polyubiquitination by double strand breaks and recruitment of RAT18, then RAT18 monoubiquitinate pCNA, and the translation polymerase are recruited. But what's happened once this polyubiquitination, this monoubiquitination is happened, is this translation polymerase are working together with the normal polymerase. That's why we study exchange rate of the pCNA and the normal polymerase and the error-prone polymerase with FRAPA. And the polymerase actually are exchanged 60 times faster than pCNA, which means they are constantly exchanged during DNA damage repair in such mechanisms. If you and this actually asked for the yesterday questions how DNA damage is repaired on both strands during DNA synthesis. If the poly can work on the one strand, and if you have DNA damage from the other strands, FAN1 is removing actually the DNA, and if you met on the leading strand, break in the leading strand, then the translation polymerase overcome pass the DNA damage and continues with the normal polymerase. Okay, what is the mechanism behind why we see that DDB2 and DDB2 subunits of one and the same complex are loading on the site of DNA damage in different times? DDB2 and DDB1 stably interact, and they can recognize on the DNA damage, UV damage on the nucleosomes. However, as you can see, DDB1 is coming about 20 seconds earlier than DDB1. And DDB1 is coming with pCNA. DDB1, except that he participate he interact with DDB2, he also participate with one ubiquitin ligase with COOL4, actually, and COOL4 also come with the pCNA. This means that the mechanism is DDB2 recognize the DNA damage, but after that DDB1 is coming with the pCNA and COOL4A to degrade DDB2 and to make possible actually repair of the UV damage. And the third phenomenon that we see that actually the resection is coming 600 seconds later than recognition of the double strand breaks. What we see that actually the recruitment of RPA negatively correlate with removal of the pCNA. To check if there is some function behind this, we put the hydroxyurea to diminish actually DNA synthesis and to delay the removal of the pCNA. But even in this case, the recruitment of RPA is also delayed, and the synchronization between these two processes continue, which means that RPA and DNA resection actually wait pCNA to be removed from the site of DNA damage, and there's some reason behind this, because actually the basic excision repair and NER have to remove the bulk DNA, have to remove the modified nucleotides before start of homologous recombination. These are my results. The first comprehensive kinetic-based DNA repair resource. The first comprehensive kinetic-based DNA repair resource encompassing the precise kinetic of 70 DNA repair proteins was generated. That reveals the detailed temporal map of the protein interactions during complex DNA damage repair. Treatment with PARP inhibitor talazoparib causes dramatic rearrangement in order of recruitment of the repair protein that could change the mechanisms and the outcome of the repair process and contribute to their anti-cancer activity. Recruitment of Rat8 in pole H is accomplished for double-strand dependent polyubiquitination of the chromatin, which significantly delayed their loading relative to that of pCNA in pole D. This delay ensures a window of opportunity for error-free DNA polymerases to repair DNA. Thanks for your attention.
Two short questions. First one, could you say please the parameters of your laser? The wavelength, the intensity, density, approximate doses total. And second question about PARP. Be careful with PARP because PARP is multifunction proteins. It's very abundant. It's like HMG, for example. HMG has 1,000 functions. PARP also has 1,000 functions. So we never know whether it's linked with repair or not with repair, so you have correlation with PARP recruitment and anti-cancer drug, but it does not mean that necessarily the anti-cancer activity is related to repair. It's multifunction protein. Have a lot of function.
Okay, the laser is 3065 nanometer lasers, which means, yeah, this is what I can say. For the dosage, we cannot say the dosage, because it's really difficult to measure the dosage on the site where you cut. Yeah, PARP1 is multifunctional proteins, this is for sure, but we measure only the activity for double-strand break, okay? For the complex DNA damage repair.
Any other questions?
You have the polyubiquitination. When does that get removed? Does that get removed only after all of the disassembly of the repair machinery?
Sorry?
When does the polyubiquitin get removed from the chromatin? After everything else is gone or during the process?
In our assay, he is not removed actually, the ubiquitin stay, because we measured this for only 1 hour and we cannot see the removal of the polyubiquitination.
Anything else? Well, thank you very much.